for the example of chain reaction in a reactor. So here is the example of chain reaction in a CSTR. Okay, so the reaction mechanism given as in the yellow table, reaction A to R, okay, and followed with the A plus R equal to B plus C plus R, and finally R produce X. So if you look at the mechanism, the first step is the reaction of reactant to produce radical species. Therefore, the reaction is initiation step. So you can write here as I, initiation step. And the second step, the reaction that produce the product B and C, and also another radical. So the second step is propagation step, and the last one, the radical reacted to produce side product X. So the termination step. And also given in the question is the rate law equation for each step. Okay, right. The first question is write the mass balance equations for species A, B, R, and X in a CSTR, assuming constant density. So, I assume that everybody should know how to write the mass balance equation, because I already give an example in the previous video how to write the mass balance equation for each species. Okay. So for question A, I leave it to you to solve the questions. Okay. Next, for question B, what is the overall reaction rate with respect to CA? So the question asks you to write the overall rate law equation. So for this case, first we need to determine which step is the overall rate law. So because overall rate law is based on the step that produce the main product, therefore the overall rate equal to the rate of propagation. Okay, for question B, overall rate R equal to rate of propagation, and it's equal to KPCACR as given in the question. Okay, then we need to eliminate term CR, because this term, okay, the concentration of radical species is very small, so we want to eliminate this term. So how to eliminate term CR? First step, again, we need to write the mass balance equation for the radical species. So mass balance for radical R, so in CSTR, CR minus CR naught per tau. So mass balance in CSTR equal to, so if you look at the mechanism, in the first step or in initiation step, R produce, so positive KICA. In the second step, R disappear and also R appear. So we can cancel out the equation. So and then followed with the termination step, R will decompose. So minus KTCR. So this is the mass balance of radical species, right? And then apply APSS approximation. Okay, apply pseudo steady state approximation CR minus CR naught per tau equal to 0. Therefore, Ki CA minus KT CR will equal to 0. Okay. Then rearrange KI CA equal to KT CR, then rearrange for CR. CR equal to KI per KT CA. Okay, then next we can insert the term CR into the overall rate. So overall rate R equal to KP. So KI per KT CA square. Okay, macam mana dapat? So this term, this CR, we replace it in the overall rate law equation. So overall rate equal to KP KI per KT CA square, which is second order reaction. Okay, so second order reaction. Alright, next we need to solve the reactor design. Determine the residence time or space time tau for 90% conversion. So given, okay, for question C, X equal to 0.9, CA naught 2, CA naught equal to 2 moles per liter, and then the rate constant KI 0.001 per second, rate constant for propagation step 20 liter per mole per second, and rate constant for termination is 0.1 per second. So how to calculate ataupun how to determine the residence time or space time for the reaction in CSTR? Okay, from question A, we already have the mass balance for each species. Is it related? But based on the mass balance equation for the reactor, it should be based on the overall rate reaction. So therefore, from question B, we already have the overall rate law equation. Okay, from B, R, rate reaction equal to KP KI per KT CA square. So we have this rate equation. Then how to determine and how to relate it with the mole balance equation ataupun mass balance equation of the reactor. Okay, for CSTR, CA naught minus CA per tau equal to R. Okay, based on the decomposition of reactant A. So we are going to use this equation to determine the value of tau. Right. So, okay. So CA naught minus Ca per tau equal to Kp Ki per Kt Ca square. So just rearrange the equation so we can determine the residence time. So tau equal to Kt per Kp Ki Ca naught minus Ca per Ca square. Right? So Ca should be no problem because Ca equal to Ca naught 1 minus x, and the conversion given, Ca naught given. So 2, 1 minus 0.9. So it's equal to 0.2 mole per liter. So just insert all the value given into the tau equation, then you will get tau for the overall reaction, because overall reaction is based on the decomposition of A, and is equal to overall rate law equation. So we use this equation, okay, which is similar with this one. And finally, for question D, so the question asks you to determine the concentration of radical species and concentration of side product X. Okay, so for concentration of radical species, we know that for the radical species, if we apply pseudo steady state approximation, okay, from question B tadi, Cr equal to Ki per Kt Ca. So we already have the value of Ki, Kt and Ca. So just insert all the value, then you will get the concentration of radical species. Okay, for Cx, okay, the mass balance of X, and this will also answer from question A. Okay, mass balance of X, Cx minus Cx naught per tau equal to Kt Cr. But the concentration of X at initial, of course, equal to 0. So, Cx per tau equal to Kt Cr. Okay, then just rearrange. So, Cx equal to tau Kt Cr. So, tau, we already have the value from question C. Cr from the previous calculation. So, just insert all the value, and then you will get the value of concentration of X. That's all.